Tom. All right. Oh, did I not copy with? That's the same. Okay. My phone is going off. I haven't received mine yet. Sometime. Okay. Let's see. Where was I? All right, let's get started. An inductive RL circuit will result in an inductive circuit will have a lagging power factor. We covered that one of the first things this morning, or something. We've covered that a couple times today. Eli and ICE. It has whether it's leading or lagging is what the current is doing. If the current's lagging the voltage, it's a lagging power factor. If the current's leading the voltage, it's a leading power factor. Eli the Iceman. Remember that. A highly inductive 25 kilowatt load is operating at a power factor of 63%. What value CK-VARs is required to correct the power factor to 95%? All right. I keep seeing a loading thing. That's weird. I hope the video's coming out good. No, it's at ultra low latency. Oh well. Oh, I'm gonna need to show you some math. Oh, man, I was excited. I was pretty sure I hadn't put any math in this one. All right. So, you've got... Let's do this. And somebody is blowing my phone up. So I'm pretty sure the three of you already know, but you know, since we're moving the test up, or not, we're making you turn it in a lot quicker. Oh my God. If you get your test mailed normally because you live a long ways away, just, you know, don't worry about driving it back over here. Just get it, do it, mail it back. All right. We understand that process takes longer. Okay, so what numbers are we working with? 25. Okay, so a trick here is ignore the kilowatts, the kilowatt part of it, because everything you're working with is in kilo, so it's going to make the numbers a lot smaller to have just VARs and watts. So we're going to use 25. We have 25 watts. We are at 63%. So whatever the total is 63%, or this 25 is 63% of, so 25, is that times? No. Divided by 0.63 equals power total, or applied, apparent. So 25 times 0.63. 15.75. So what we've got is 15.75. That's not right. We went the wrong way. How? Oh, I hit multiply. Hang on. 25 divided by 0.63. 39.68. That's so much better. All right, so now we need to find capacitive power. So to do that, we will go ahead and do Pythagorean theorem, but we'll have to solve it for, so PC is equal to the square root of 39.68 squared minus 25 squared. And that formula written out looks like this. Square root of that's that formula. All right. So that gets us here. Let's do the math. Drop that down a little bit. Let's move it over. So we open parentheses. No, we don't need to open parentheses. 39.68 squared minus 25 squared equals, and then we'll square root that, 30.81. This would be, now that's kVARs, but you know, 30.81. So this is what we're working with right now. So what would we need to make this 95%? So what we have is 30.81. So I'm going to use green as what we want to get. 25 divided by 0.95. So this will be the apparent power at 95%. You'll see it's a lot closer. Oh, I closed the calculator. You'll see it's a lot closer to 25. $26.31. So now we have 26.31 volt amps. So now we do that calculation again. PC is equal to the square root of 26.31 squared minus 25 squared. And we'll plug that in the calculator. And once we have where we are and where we want to be, we can subtract them from each other. So 26.31 squared minus 25 squared equals And the square root of that is 8.19. Oh, excuse me. Okay, we got and so the difference between these two is what we have to offset. So to get from 30.81 capacitive VARs to 8.19 capacitive VARs, you have to apply a certain amount of inductive VARs to the circuit. And that's voltamps reactive. It's inductive power. You have capacitive power, it's offset by inductive power. So we need to apply 30.81 minus 8.19. We need to apply 22.62. We'll call that blue. 22.62 L VARs. Inductive VARs. So let's go back to our lesson. 22.75. That's pretty close. If you go back and watch some of last class's videos, there was a question probably exactly like this. And they have a suggested way to solve this that does it all in like one step. And it might be in the book. I don't know. But what I showed you is like the several steps easier to remember. For me, anyway. Because it's just, okay, let me find out where I'm at. Let me find out where I want to be. What's the difference? This is how much I need to offset. Okay. Question 3. Digital logic probe is a DC voltmeter. Nothing more to say there, really. It's all it does is detects voltage. The total current in a circuit containing a 2-wire solid state. So this one. A 2-wire solid state switch is like a smart switch that goes in line but doesn't have a neutral. You just connect the hot and the hot, or the hot and the switch leg, and going to operate. And so it's going to use some amount of amperage, or it's going to pull amperage, it's going to use some amount of power for it to work. And so it's going to add to your total circuit load. So it'll be the load current and its operating current is what that's called. And the kVA ratings for 3-phase transformers are about 50%. Yeah, so 3-phase gives you about 50% power boost for the size that your motor is. So generally it's better to run things on 3 phases than 2 phases, or than single phase. But that's not always an option. It's more expensive to do a lot of times, but overall, there's a reason why industrial facilities go 3-phase instead of single phase. There's a reason why most commercial buildings are 3-phase. It's just because everything operates more efficiently at 3-phase. Yeah, and that's because in the sine wave you don't get in 3-phase, it never hits 0. It's always, they're 120 degrees apart, so it always just, it's riding on the highest phase at the moment. And the individual phases drop past 0 and stuff, but that doesn't matter to the motor. It's always being pushed, as opposed to a single phase motor that is pushed, intermittently. All right, that finishes that. I'm going home. So I will talk to you guys later.